It is my great pleasure to welcome Dr. Lloyd Colegrove to the SoothSight podcast. He holds a PhD in chemistry, chemical physics, and spectroscopy, has dozens of publications, and is a bona fide expert in AI. Lloyd recently retired from Dow Chemical, where he spent nearly 30 years and held various leadership roles in data services, fundamental problem solving, statistical and modeling services, quality, and R&D. He is responsible for creating several departments, and he was the first person to bring Process Chemometrics, or as we call it today, AI, to Dow, and potentially the first in the chemical industry more broadly. Dr. Colegrove also founded the cycling team at Dow, which has raised several $1 million in the fight against neurological disease, and he is a member of the National MS Hall of Fame. Lloyd is a man of immense ability, and his latest endeavor is assembling a museum-quality 16th century Spanish galleon. Dr. Colegrove, thank you so much for joining us today.
Thank you, Chris. If I may correct the record, I did not bring chemometrics to Dow. I merely recognized a unique opportunity for it to the gentleman who did, to the group that did bring it to Dow, and launched them on a completely new path in aiding the chemical industry from that. So I just wanted to clear that up initially, because I'm not a chemometrician. I just understand the power of it.
Thank you for clarifying. So the famous statistician and chemist Ronald Coase once said, if you torture the data long enough, it will confess to anything. So with that in mind, can you tell us about a time when you were able to uncover a surprising insight or solution through careful analysis of data in your work?
I can think of dozens of times, but I'm going to go back to the first, Chris. Back in around 2002, I was a newly established quality director for business within Dow. And into my office walks the vice president of the business, manufacturing vice president, and the tech center director. And they look at me in my brand new job, and I'm a little intimidated. And they say, well, we've gotten a customer complaint from one of our most significant and highly technical customers about a product we sent them. We've already done, the plant's already done the discernment on the product that we sent them, and all the quality parameters are perfectly within spec, yet the customer is suing us for a large amount of money because we basically destroyed an entire product run for them. What can we do? And they're staring at me. So I said, well, let me go take a look at the data and come back in 30 minutes, and I'll let you know if I have an idea. And that was a pretty gutsy claim at the time. But what I did was I took out my most sophisticated data analyst tool at the time, something called Excel. And I did an immediate download of about 6 months worth of data from the plant, the quality data from the plant, into my Excel spreadsheet. And because I know how to do it, I programmed Excel to plot X versus Y on all these parameters. So all these little graphics started showing up. And all I'm looking at, I'm not doing data analysis at this point, Chris. All I'm looking at is data clusters. And the clusters, it looked like a shotgun. I ignored them very quickly because that didn't mean anything to me. But I was very interested in the data where I did see correlations. I didn't care what the correlation was, but I saw correlations. So then I went into Excel and said, all right, reveal the lot in question, the one that has annoyed our customer to the point that it's going to cost us a ton of money. And a little red dot appeared on all these various graphics that had appeared on my screen. And I noticed that in the shotgun patterns, it was just in the shotgun pattern. But where there was correlation, the dot was off axis. So if you had a correlation of data running lower left, upper right, it was in the lower right or upper left corner. And when I looked at some of the parameters, I realized that, by golly, we were violating a fundamental law of thermodynamics to get to that point, meaning that the data point couldn't possibly be right. Well, except that it was right, but something was wrong with the process. And I discovered by doing this over a period of 2 years that it had been going on, I'm pretty much sure, for the life of the plant randomly. Nobody knew. Well, these two gentlemen walked back in and I said, guys, you've got a problem you're not aware of in your plant. No one's ever complained about it before, but now that your customers are getting more sophisticated, somebody's noticed. And their first question is, well, what on earth are we going to do about this? We don't know what's causing it. We don't know when it happens. In the univariate world, everything's in spec. Everything's in between the high and low on all these different parameters. And I said, I've got an idea. And I said, I'll tell you what, but you guys need to start working on figuring out what's wrong with the process. I'm going to go solve this so that no customer gets insulted by it while we're figuring it out. Because by the way, I figured with the data, we could solve the immediate problem of not surprising customers. And the long-term problem was going to take a couple of years, I was pretty sure. Well, anyway, I called up a young man who was doing multivariate analysis for our process group, because multivariate statistics, the things we refer to as AI blithely today, we've been using that in process control for decades. And I said, I need you to come here and I need you to take a look at this massive data set. I want to model the data set, especially around these correlated variables we have. And I want the model to tell me when the data points going outside of that cluster of data. And he said, okay, sure. And we created the model, we installed it into LIMS, we turned it on, and immediately the model started alarming. Every batch that came in, it got further and further away from the center of our model. And we at first thought we'd made a huge mistake until one of the operations leaders in the plant called us up and said, no, turns out we do now see a problem you detected 2 weeks prior. And AI in manufacturing was born in my company at that point, because it would, not only did it reveal things in the data that we did not know and had not known since the plant had been built, it gave us an early warning sign to problems if we applied the right tools in the right direction, weeks, if not months, before the problem actually started creating a serious problem in production, and absolutely validated the approach. An approach that is not simple because it's not univariate, it's not what every engineer or operator expects, and that's why it was so wonderfully, serendipitously marvelous to arrive at this conclusion. Chris, we actually published an external paper on that particular project I just described to you in 2007, and it was a highly read application of multivariate statistics in process quality control at the time, because even though I knew that the capability was able to do what we wanted, I did not know at the time that nobody was actually applying it this way. And so ours turned out to be the first public admission that we could now use what we later called AI to help monitor our batch process. It's easy to do continuous, by the way. This is batch. Help us monitor a batch process to great efficacy in the plant.
Very interesting story. So maybe fast forward a few years, can you talk about your experience leading data services and the fundamental problem solving within the Analytical Technology Center at Dow?
So the first thing I did, well, the type of work we accomplished in this one business caused other businesses to say, hey, Lloyd, we'd like you to come do that here. And so as my responsibility expanded, we started getting into all sorts of issues in other businesses and other processes around the globe. And I was using a loose knit group of very, very bright scientists and engineers to go after significant problems in the plants. They'd been doing this kind of on their own anyway. And when I got into a point where I decided I wanted to do that kind of work formally for the entire company, I got together a few of these people and said, we're going to call this fundamental problem solving, and we're going to start going after those multi-effect or problems that kept recurring in the plants that the plants weren't capable of solving themselves. And why was analytics so important to this, Chris, is the very first thing we would always do when we got called in to a chemical operation with one of these types of serious problems. So we'd send the data people in, ask them to take a look at the entire data signature of the plant and start helping us understand where there might be anomalies we needed to go explain. So I developed the capability of fundamental problem solving with a bunch of collaborators. They have actually written a book on the technique of fundamental problem solving in the chemical industry that you can now find out on Amazon. But then after that, I went back to these data engineers and I said, hey guys, we need to now figure out how to replicate your capabilities, the individual PhD'd, mostly chemometric, multivariate, AI type people. We need to figure out how to propagate you across the company without having to hire 1,000 of you, because you can't do that. These people just don't exist at that rate. So honestly, in comes Soothsayer, in comes a bunch of other different types of companies, because we're looking for capabilities that maybe some of them we could do on our own. Some of the things, like when we first talked to you all, we couldn't do that. And you, I think you provided us a lot of service in that area. But we created a larger group to go after the more harder data problems. And at the same time, we were looking for new tools and new approaches that might be adopted by a very intransigent workforce. And that effort grew into two areas, fundamentally. What I call chemometrics, but we call AI generically, and then what I would term real-time analytics. So real-time analytics is there's different types of analytics. You've seen the pyramid of the 5 things, and there's reacting to the data when it says, there's a problem, you move up. Well, at some point, you need a system that's monitoring the data now, informing you of things about the data, and giving you options about what you need to do to get the process back in control. That's real-time analytics. That is not a red light on your control board beeping at you, so some operator or engineer walks in, turns it off, and then goes back to their coffee. Or if you walk into lots of control rooms in any company around the world, you will see duct tape over certain sensors in the plant because they haven't turned the thing off and it's been flashing at them for a decade, right? I wanted something that was attached to the data streams in the plant historian now, monitoring not only what's going on now, but how it's monitoring it versus history, and then giving the user a better idea of when a plant is actually trending out of control versus just responding to the random nature of the data within the plant. That is real-time analytics. So these became two different issues because chemometrics helps us predict, helps us look forward, and helps us understand the big picture, while real-time analytics allows us to stay focused on the operation of the plant as we move forward. And let's remember that chemical plants today are probably run at a level of human resource that was half to maybe a third of what we used to do in the 80s and 90s. My entire career in Dow, from 1991 to when I retired in 2020, was a huge effort to cut people out of cut staff. Everybody's doing it, not just in our chemical industry, right? And so therefore, the problem is we didn't change our behaviors in how we transmitted information, how we taught our new employees, and people started running plants based on what we would call maybe voodoo science or tribal science. You know, if you have this problem, this is the solution. And my focus was trying to get people to bring data forward and then validating these tribal beliefs with the data. And if we could validate it, we would ensconce it in some knowledge capture mechanism within the plant, or we would destroy the belief because we couldn't find data that would support that approach. And so I developed real-time analytics, chemometrics. We had a couple other functions within the group that had to back up all of this. I don't believe in buying software from anybody and just throwing it over the fence. So whenever we would bring new technology into Dow, we'd have to assign people that were responsible for making sure that it lived and grew, and that was another function as well. So it was a complicated mishmash of a bunch of different things to try to support the analytics digital thread as we move forward.
I want to come back to the real-time piece and people in the age of AI, but just broadly, I'm wondering, how is AI in chemical manufacturing different than some of the other verticals or industries, or even are there certain constraints or challenges that you have to account for that may not exist even in other forms of manufacturing?
Okay, yes, AI in the chemical industry is different in one fundamental thing. If you use AI to predict human behavior, like they might do in the medical field or in insurance or in big box stores trying to figure out what you're going to buy, it's okay to be wrong because the only thing you've done is inconvenienced your supply chain. If a chemical plant is wrong in its application of AI, only bad things happen. People can get killed. You could insult the environment. You could threaten nearby communities. You could shut down and annoy your customers. There is nothing good that comes out of being almost right using AI. Therefore, AI has to be curated in our industry. You have to have domain knowledge because AI coming in and telling you something that you should have already known from the fundamentals means you don't know the fundamentals. And if you don't know the fundamentals, you should not be running the plant. So when companies would come in and try to sell us their AI and say all these wonderful things it could do, we were already using our own internal version of it. And we're looking at them like, you're crazy. I don't want AI to confirm the first or second law of thermodynamics. What I do want AI to do is help me identify data trends and things I should be paying attention to, and maybe go figure out what's causing those. It's different than, say, Amazon or Target or anybody monitoring my buying habits, right? Because if they think I'm buying parts for a 16th century Spanish galleon, which is my latest little winter hobby, they may think I'm going to buy more. Well, what they don't know is I've already got everything I need. It's going to take me a year to even get to the point of near completion on this project, and I'm not buying anything else. Well, they stock up that stuff. Okay, that's a supply chain issue. But if I'm trying to do something that is under pressure, temperature, reaction kinetics, or anything like that, and the AI is wrong, it's not good. So we had a hard time initially convincing people that would come in that while we understood their excitement over bringing AI into our industry, they didn't understand our industry very well. By the way, Chris, your organization did. This is why we continue to talk to you.
This is not a paid
but it is very different. The way you would manage your AI in the chemical industry and in the process industry in general would have to be different.
So in your experience, and what are some of the biggest challenges that you're facing in the chemical manufacturing industry in terms of things like big data management and analysis and modeling? So, I mean, you don't have to go down this route, but for instance, I saw somewhere where you wrote about the bottleneck between IT and manufacturing functions.
Okay, so there are a million reasons why it's challenging, and I've written a paper about it. But let me just say that one of the biggest challenges in the chemical industry is that the digital thread, which runs a chemical plant, it's a very complex collection of a bunch of different operating systems. We've referred to the manufacturing piece as MOMS, by the way, MOMS, but it's bigger than that. That is something that has grown out of the initial efforts to automate chemical plants in the industry, probably starting in the late 50s and early 60s. By the mid 70s, companies like Dow actually built their own operating systems, or automated operating systems, because there was nothing commercially available out there. So as you continue to morph through this process, today, by the way, I think we're using ABB and suppliers like that to help us with this. You still have an enormous investment in what you've already got in place. So you can't just replace these things willy-nilly. And oh, by the way, go try to resensor a plant. That's just be ridiculous. Coupled with that is the commercial side of the company has to link into this system, and all the commercial databases, what's called order to cash, customers coming in, product going out, the company getting paid back. That is also kludged together with a bunch of different systems that do various things. And it is that situation, that status, that creates a huge inertia against bringing in wildly new things to basically boil that ocean. You aren't going to do it, because not only would it be very disruptive somewhere in the data chain, but it would also potentially be cost prohibitive to do, simply because of what you've got invested in the existing infrastructure. I would like to say one other unique thing about the chemical industry. So this applies to both questions you just asked. The amount of data that we produce is enormous. We have what is it? Analysis paralysis. Too much data. What I worked on in Dow for 20 years was to try to bring order to the massive collection of data that was coming into the plant, and helping engineers by bringing in new systems that would pay attention to data they never looked at, and just alert them when that thing is going wrong, because usually it only gets the attention of the engineer when there's a real big problem, right? So how do you manage that massive process? It's made worse by the fact that data historians, Aspen Tech, OSI, all these things mainly run process data. You have process analyzers that may or may not even be tied into that data, going out there and monitoring your plant. And then you have a lab over here, maybe next door or maybe down the block, that's doing your data during a shift, right? So 3 to 4 times a day, which is not even data-wise lined up with your continuous data in your plant. And how do you manage all of that? Okay, it's a problem. That's the biggest problem. And now I'm going to tell you something even funnier, is that if you wanted AI to run a plant today, to do all the decision making, even the chemical industry doesn't produce enough data to allow the model to do that with 100% accuracy. And 99% accuracy is not good enough. So lots of challenges. In my industry, we have to raise our workforce's awareness of what AI can do, but then we have to be very careful how we apply it. Chris, it's a very topical piece at this point, because Microsoft's boss, whose name has just completely popped out of my head, or he was their boss, is going on ABC talking about the threat of AI and the possibilities of AI. We've known about that for dozens of years, because we can use it. It's very effective, but don't walk away from it. Don't leave it to its own devices. Don't. In the chemical industry, we have already understand that very, very well, and that makes us. That means it becomes a worker-intensive activity to bring value in certain cases, but not in all cases.
How do you see these challenges evolving in the future? And are there some best practices that come to mind? And maybe also if you could share any particularly challenging manufacturing problem that your team tackled, and how you were able to go about solving it.
Well, so many come flooding to mind. The best practice for in any AI project is to first go turn on all the data and look at it, and get the data. Interrogate the data, like you started out with the introduction. Interrogate the data till it starts revealing its secrets. Once it's revealed its secrets, the problem then is it's usually not so obvious what that signal means. So then you bring the appropriate knowledgeable engineer on a particular area of technology to help you understand what that signal is telling you about the process. And remember that processes are very complex. They have many unit operations within a process, and a problem you see down the line may or may not have anything to do with something that's happening immediately around the process. It could be a problem earlier on. You also have to fight emotion, because people are always willing to blame someone else for a problem they're seeing and not see the opportunity sitting right in front of them, and that's a challenge as well. So in problem solving, we have used AI to help us understand that over a period of time, a plant stays within a particular factor space of the data, an n-dimensional factor space of the data, and then mysteriously for a while moves to someplace else and then comes back. Now, if it was doing that constantly, it would all be in the same cluster, because the uncertainty in all that data would say, well, the process is acting significantly. But if you see the data clusters moving substantially out of that cluster, that's a very clear signal that something is happening that you are not in control of and you don't know anything about. And then you need to go find out why it's doing that. By the way, Chris, in the olden days, back probably in the 60s and 70s, really bright engineers would go into plants and stress them to see them move these different directions, right? And they would learn how the processes ran doing that, which perfectly valid as long as you don't destroy product or harm anybody. But I'll tell you, in the 80s and into the 90s and into today, you don't do that to a process anymore. You'd probably get fired if you did that, because the plants are generally running as fast as they can, trying to make product. We're trying to meet the expectations of our investors across the entire industry. And so data, as you just remind me, proper application of AI can help you play with the plant without actually endangering business, people, environment, or communities. And so there's an opportunity. In terms of particular plant problems, it really is applying AI to look for those signals and then understanding what those signals mean and what their impact on the plant is, and then putting in control processes around those new signals. And oh, by the way, back to my real-time piece. So they handed off the real-time people. They put those metrics within the operational dashboards or maps in the plant, and the plant doesn't have to keep looking at that data, but the minute something's going wrong, it'll alert them and let them know they need to go back and pay attention to that.
And I want to stay on this thread of real time. So in one of your publications, you talk about real-time analytics leading to a more proactive and productive approach to manufacturing. Can you elaborate on this and how you see real-time analytics continuing to shape the future of chemistry and related industries?
Sure. I'm going to take the simplest example. I'm known, when I speak in front of public audiences, Chris, I bring a bunch of little squish balls into the room. They're stress balls, right? And I hand one out to everybody in the room. And then I get some unknowing person to play with me, and I hand this person a box, a file box. And I say, welcome to my operational paradigm. This box you've got is an Excel spreadsheet, okay? Now stand here in the middle of the room. And then on the count of three, I tell everybody else in the room to throw their ball and get their data, get their piece of data in the box. They're either an email, they're a sensor, they're a lab piece of data, they're an instruction for the production leader and engineer. But this engineer running the plant is responsible for all this data. Here it comes. How many balls do you think actually make it in that box, Chris? Very few. Out of 450 thrown at a conference in Italy, I think about 15 actually made it in the box. Now, what do you see in this picture? You see an engineer standing there looking a bit shell-shocked because he or she didn't know what was coming. And you see me and the entire audience laughing because around them are hundreds of balls that didn't get into the box, which means hundreds of pieces of data and information they couldn't manage with their tool, with their Excel spreadsheet. So then I look at the audience and say, okay, if there's a problem with the plant and I walk into that engineer's office and ask them what's wrong with the plant, what are they going to do? They're going to look in the box, and everybody looks in the box. And I say, well, but what about all the rest of this data? And the engineer, if they're thinking rightfully, says, I'm not paying attention to that data. And I say, exactly. So what if I send a chemometrician in and they do a broader data analysis, do something the engineer at the board is not capable of doing because we didn't give them the tools or the training or the preparation to do this? What if that chemometrician or AI expert walks to the other side of the hall where there's a ball laying on the ground, grabs it and comes back and says, this ball is the problem in your plant? Well, the engineer will say, well, how am I going to know that? Because I'm not looking at that data. Exactly. Okay. Now, the other thing I do is in the one box I made, I have a false bottom. And if I have a red, yellow, or blue ball, let's see, yellow and blue makes green, right? So I'll pull out a green ball and say, oh, this is a different color than all these other balls. What is that? And everybody in the audience is going, oh, I don't know. That's AI. That's the correlation data point between those other two colors, between those two pieces of data. And a bunch of those data points are really important as well. So the real-time component of what I was trying to do was to create a tool that would give you multiple different looks at your process depending on how you want to look at the data. So let's use the simplest form of this, which is a dashboard. When we would go in with the tool that we selected to do this real-time analysis of our data, we would turn on we would get a dashboard with a bunch of different metrics in a particular unit operation, and we'd ask it to evaluate that data based on control, based on trending. Is it under statistical control? You'd set your limits around it. Oh, and by the way, you would set the limits about how the plant was supposed to run, which most people forget. And typically when we turn the tool on, after we got all the data into the tool, everything's red. Some greens, but mostly everything's out of control. Well, then we say, all right, why don't you guys go in and get all that in control? And after 2 or 3 weeks of working on those data sets, everything's in control. By the way, the first thing you notice is you have to look at fewer measures, because as you control one, everything else corrects. And so all of a sudden the user's like, hey, if I keep this under control, these things stay under control. Great, get rid of those. Don't put those on my dashboard. Well, I took a picture of a before and after of one plant, one unit operation, of them going through this exercise. Complete chaos on one side and green and beautiful, and the plant's running better than it's ever run before on the other side. I took this to the vice president of manufacturing at the time and I said, hey, which way do you want us to run our plants in the future? This way or this way? Of course, he said, I want the one where it's running within all the required specifications. Well, you can't do that without my tool because people can't see that data. Now, I'm going to tell a story on a petrochemical company that showed up at a conference in Houston one time at the AICHE meeting, where some of my colleagues were presenting what we were doing in real-time analytics, and they showed this beautiful slide of chaos and control. And they spent a lot of time talking about it. And the chief engineer for this company got up in front of this huge audience of people and said, well, clearly it's obvious that the people on the left didn't know what they were doing and the people on the right, they did. Why is your tool so special? And the two guys in front of this massive audience were stunned. They didn't know what to say. And I got up and said, may I take this? May I take this? And I walked to the microphone. The difference is it's the same people. What we did was changed how they looked at their data. That's all we did. But see, the mindset presented by that chief engineer from this very august and very respected manufacturer wants to blame the people for the bad decisions they make, when I learned through 30 years at Dow, it's less about their desire to make bad decisions when they get up in the morning than their lack of information and a way to manage it. And so what AI and real-time analytics can both do for us is allow our workforce a better way of managing data and making decisions, bottom line.